So now I will mute myself and I will let Professor Chernikov to start his lecture. Thank you so much for being the first one in this series of lectures of Nano-Flatlands beyond graphene. Hopefully, this 2022 edition will be in person.
Thank you very much, Andres. It's a great pleasure and, of course, also an honor to begin this lecture series and talk series here virtually. And welcome everybody. And good evening, good morning, depending where you are. In this talk, I would like to introduce you a little bit to some of our recent endeavors into the field of mobile excitons, and in principle encompassing something that is quite dear to our heart in the last couple of years, combining transport and optics to study a host of phenomena that is particularly interesting in this class of two-dimensional materials. And in this talk, I will start with a rather broad introduction, and many of you, of course, working in the field will be familiar with probably everything that I will just review and recall in this section. And then I would like to present you and focus on two aspects and two studies. One is creating unidirectional channels for excitons, so actually guiding their movement. And the other one is concerned with the nature of exciton propagation and rather kind of trying to find a proper fundamental description, how we should think about transport of optical excitation in 2D materials. I would like to thank a lot of collaborators who contributed to many aspects of the work that I want to present here. In particular, our theory colleagues Mikhail Glazov from Joffe Institute and Ermin Malic from Philipps University at Marburg, as well as Paulo Faria Jr. from Regensburg. And we have collaborations with Florian Dillenberger now in City University of New York and Archana Raja in the Berkeley laboratory and BNL. So our group is focused on studying optical excitations in matter. This is kind of our main focus, and we're looking in particular at the role of electronic many-particle interactions. So what happens when many electrons and holes interact with each other, and what are the consequences? We're looking a lot at nanostructures, kind of historically, mostly two-dimensional systems, but moving towards 1D and eventually 0D as well, both inorganic ones and maybe some of you can guess from this figure, also inorganic organic hybrids of perovskites. And during our recent years, we were looking with particular detail at how energy and information is transported in the system that is imprinted by optical excitation. In general, if you think about optical excitations in nanomaterials, it doesn't really matter. We think about 0D, 1D, or 2D. Light comes in, it's a semiconductor, so it raises an electron from occupied valence band to unoccupied conduction band. And that leads to a presence of charge carriers, of course, as a consequence of absorbing photons. But in most of the systems, maybe even in all of the systems, the interactions are strong enough so that charge carriers usually don't exist by themselves, but they bind together in the so-called excitonic complexes that are very well known for many, many decades in different material systems. And then these charge carriers exist as these coupled and bound states. And then, of course, if we think about transport of energy, but also information, which can be encoded by the spin degree of freedom, as indicated here in the middle, or maybe by a Valley degree of freedom, that's particularly important for 2D system, then the excitons are the actual carriers of this information and, of course, of the energy of the excitation. And in this talk, of course, I will focus on my area of expertise, which are the 2D materials and 2D semiconductors in particular. So the family of 2D materials is, of course, very, very rich. And there are many systems with very interesting and peculiar properties, both as bulk materials, but even more important as individual monolayers or a few layers. And in addition to semimetals, insulators, semiconductors, there are more exotic materials. There are topological insulators, superconductors, magnets, hybrids, and so on and so forth. Hundreds upon hundreds, potentially interesting 2D systems. And on top of this come more recent developments where you combine them into artificial heterostructures with a lot of opportunities for basic physics and technology. Now, if one wants to do optics and in the visible spectral range, then usually the family of transition metal dichalcogenides comes to mind. There are other materials that absorb in this range, but this is the most prominent family. And this family has been known around for many, many years. People studied it in the middle of the last century and towards the end quite a bit. In particular, as bulk, also as were thin layers, maybe some monolayers, who knows. But most of the interest came on the heels of graphene, and especially where people realized that when you go from thick crystal to a monolayer, you get a lot of rather peculiar and interesting properties. There are changes in the band structure. This material becomes a direct gap semiconductor in many cases. The interactions are very strong, which will play a particular role also for my presentation here. And there is this coupling of spin and valley degrees of freedom, which motivates a lot of people to consider the system also for technological implication in the context of quantum information storage and transport. Along these lines, if the materials are handled in a specific way, and of course now as a community we learn more and more how to make high mobility devices, and with a lot of opportunities, of course, for optics and photonics, because there is strong light matter interaction in many cases, and you can kind of squeeze it in on a very small scale. There are all sorts of opportunities for environmental engineering, be it dielectric, be it chemical functionalization, and of course, artificial heterostructures play a big role. Yes, exactly. To support Andres, I also forgot to say it. If anybody has questions in between, please let me know. So, and then we can also discuss during the talk a little bit. Yes, so just go ahead if you have any. So another advantage, if we think about 2D materials, and this is something that, again, is not new, but it's important to emphasize that it's relatively easy to gain access to good systems and high quality crystals, especially for basic research. You see here examples from our group produced by Jonas Ziegler of single crystals with hundreds of micrometer sizes. But of course, there are many ways to do it epitaxially, and this is a field which is also rapidly growing, because that what would lead to scalable approaches, also for potential applications in particular. But for us, if we do basic science, it's usually enough to use something like an advanced version of the Scotch tape technique. In fact, well, I mean, it would be weird not to mention that we basically stamp the way Andres was stamping many, many years ago, and it works very well. Now, if you look actually even here, just at the fact that even if it's a monolayer, you can see a contrast with the bare eye. So we need the microscope for the spatial resolution, but the images are not enhanced. So you can see the contrast. So you already can guess that the light matter interaction is strong. And in fact, if we look at something like room temperature absorption, one realizes quickly that yes, it's a semiconductor. So there is some form of optical band gap over here. It's a WS2, by the way. But the overall absorption strength is very high. So we're talking about 10–20% easily across the visible spectral range for a material that is, again, much thinner than a nanometer. Then if we go to textbooks and we think, okay, how should a two-dimensional electronic system behave with respect to excitation by light? Then we realize that there shouldn't be any peaks as a rule. Yeah, so for extremos that are parabolic, we would expect something like this. Yeah, so a step type of density of states that should translate into optical absorption. But obviously, you know, we can try to match it, but it works only so far. And the reason it doesn't really work and doesn't explain the peaks is because this is a single particle picture, but interactions are important, and interactions are responsible for this type of optical response. And the interaction between the carriers I'm talking about here is the Coulomb interaction. And in principle, for many of the problems, you can think about it as a far field repulsion or attraction of charges of equal and opposite sign. But of course, in quantum mechanics, if we want to calculate things properly, exchange is important as well. If we consider Coulomb interaction, it has several consequences, and also with respect actually to free charge carriers. But here I would like to focus on the attractive part, on the appearance of excitons, which are kind of hydrogen-like Coulomb-bound pair in these materials. And to understand their properties, one usually considers two aspects. First is quantum confinement, but second, quite important one, is the screening from the surroundings, the fact that the interaction is three-dimensional even if the carriers are confined. And that has a consequence of very strong binding energies because the surroundings are usually weakly screened. And then there are certain peculiarities associated with this dielectric structure regarding the Coulomb law. And typically we're thinking about quasi-particles that can be described by a wave function along this line. So the hole, for example, sits in the origin, and then the electron can be found somewhere within the first couple of nanometers. So relatively small quasi-particles, but not yet Frankel exciton if we think about organics. So in general, excitons were, over many years realized to determine the optical response in this material, and they, of course, then should govern the energy transport and spin value transport, so transport of energy and information. And that's why exciton propagation in 2D materials became more and more of a topic, initially for monolayer systems, and now, of course, more and more for heterostructures. And I would even dare to cite all the papers that are coming out every month on the subject of exciton propagation in Moray type systems and all sorts of materials. And it's interesting both, again, with respect to fundamental physics, the spatial degree of freedom, but also, again, if people think about something application like be it a detector or emitter, it's important to understand how excitations move. To study this, in principle, the methods didn't change for hundreds of years. I guess how to study diffusion and transport, you need to have something local. You need a localized excitation. You can't excite everywhere. And then you need to look and to find out a way how to detect the propagation as function of time and distance. And with respect to excitons in particular, I would like to point you out here to this paper down there. It's a review by Naomi Ginsberg and William Tisdale, very recent one, having a very nice overview of modern techniques, how to do it, especially using optics. And in our lab, we use a very fast laser. We use a far field imaging with a microscope objective, excite a small fraction of the sample, and then we image a cross-section on it on a street camera detector. The cross-section we can spectrally filter. It will become important for a later topic. And with the street camera detector, we then emit the excitons as a function of time, but also as a function of position. Yeah? So basically, to get information about this quantity and as function of time and space. A typical measurement result or image, which you will see on the street camera screen after sufficient integration, will look like this. So on the y-axis is the time. At time point 0, the laser comes in, and then the excitons appear and are excited and start to emit. And then over time, the emission decays because, of course, they recombine for all sorts of reasons. Here, by the way, it's a measurement of a suspended, unencapsulated monolayer sample at room temperature. To visualize diffusion, in many cases, it's helpful to normalize the signal at each time step, and then you see how the cloud of the excitons becomes larger and larger with time. For quantitative analysis, one would take the cross sections, one would fit them with symmetric functions, usually Gaussians are an appropriate choice, and then one would plot the area as function of time. Yeah, so while we detect in one dimension a cross section, but the area is the relevant parameter, so how the area changes. And if the transport is diffusive, as it is shown in this case, then the area grows linearly with time. Yeah. For example, in ballistic case, it will be a square dependence. But here's diffusion. So it's basically a random movement of excitons exploring the material. And from the slope, we can then extract the diffusion coefficient. And if you're coming from the field of electron transport, then think about diffusion coefficient as something like mobility, something that quantifies the ease of movement of a quasi-particle. There are a lot of phenomena to explore already with this type of systems. And one example would be if we pump the system sufficiently high, but not super high to destroy it or do something with it, then one can see that, for example, a ring-shaped pattern evolves, and which is a quite peculiar phenomena, because to explain it, we need to consider some form of memory effects and collective phenomena. And on the other hand, we have to think a lot about environment. Yes, we need to think a lot about the potentials in which these quasi-particles move. This is as true for electrons as for excitons. And in case of excitons, one particular aspect that determines this energy landscape are fluctuations of the dielectric environment, which are quite strong, and they have basically can produce disorder potentials on the order of room temperature and far beyond. However, luckily in the field we have a solution, and this solution we actually had before we, properly understood, I guess, what was going on, and but by creating homogeneous dielectric environment using HBN from, well, as many people in the community know, also from a very particular source, from Takashi Taniguchi in Tsukuba, Japan. But by doing that, we not only get rid of, the substrate as, let's say, a source of charge defect or something like this, but we also create homogeneity. And then usually what one would look at spectral feature, so all spectral response gets narrow, the inhomogeneous broadening disappears. But if we look at transport, if we look at diffusion, one can realize that yes, indeed, the diffusion coefficient can change quite drastically and is improved even at room temperature by more than an order or 1.5 orders of magnitude. There is something to say about the numbers here. If we think about it kind of naively and we'll think what this number corresponds to, then we find out that this is basically the limit of the electron mobility that we should expect in a high quality sample. For excitons, this number is actually too large, and the 20 nanometer mean free path is too large. And then we explain a little bit and provide some suggestion how that can happen in this publication by Jonas Zipfel, who is, I think, as I saw before, is in the audience. Yeah. So, and Jonas is right now in Berkeley with Archana Raja. So, but the message here is this order matters, but we can get rid of. And this is quite important, because if we want to study intrinsic properties, or we want to have something fast also with the excitons, we need to take care of this order. And with that, to summarize this first part, what I have shown you is that excitons in 2D semiconductors are tightly bound and mobile. Mobile in particular, that's a key point, because tightly bound, you think about pentacene, that's tightly bound, but mobile, not so much. Excitons exhibit nonlinear diffusion phenomena of all kinds, usually associated with exciton-exciton interaction, but also probably exciton-electron. And this order plays a big role. But in the following, I want to think about this order as we want to get rid of it and forget about it for now. So what I would like to show you now is how we can actually try to guide excitons or create some forms of potential for it. So how we can influence this movement. And this work was mainly done by Jonas Sigler in our lab and Florian Dierenberger, who is now with Vinod Menon at City College of New York. And we had theoretical support, especially from Paolo Faria Jr. from University of Regensburg. So to modify exciton propagation is actually not that easy if we come from, let's say, electron transport, because with electrons, you apply an electric field, electrons are charged, they move. With excitons, we can use external fields, but it's tough. We have to think about specific designs, Stark effect, something along this nature. We can think about functionalization, so basically kind of chemically modifying the landscape. Dielectric approach can be useful, but also strain engineering. And strain played a big role in this field and still plays, because it's a very good way to modify excitations and to have this kind of optomechanical approach there. And there are a lot of ways to induce strain and also to understand what happens when the material is put under strain, tensile, or you pull it apart or you push it. Here's an early example where it was shown that applying, let's say, 1% to 2% strain is possible, reversibly so, but also that we have substantial changes of the optical band gap here on the order of hundreds of millimeters. And this we explored in our study. What we did, we started with a system that has nothing to do with 2D materials. It was a gallium arsenide nanowire, so very established, clean, hundreds of nanometer thick core shell structure with aluminum arsenide on the sides. It was many micrometers long, and on top of it we placed a 2D material but encapsulated one. So, and of course it serves two purposes. We get rid of dielectric disorder, but also we forbid and prohibit any sorts of tunneling into the gallium arsenide or aluminum arsenide substrate. And what you see here in a bit of a fancy 3D version is, and you may have guessed by colors, it's an FM image of a nanowire covered by this encapsulated WSA2. And while the dimensions are relatively small, we can still use far-field optics to get an idea of the strain potential. And here we can cool it down. And this is quite important. So because the overall amount of strain as estimated from the energy shifts of luminescence, as you can see here, is relatively small. So we're talking about 0.1, at most 0.2%. But because the lines are so narrow, we still see a very distinct shift of all resonances. And this is an idea how a strain potential could look like. It doesn't mean it has to look like this, but that is kind of the simplest way we can describe our measurements, considering the convolution with the optical resolution. So we're talking about a groove for excitons in the 2D material of something like 10 MeV. And here is just a quick example what encapsulation does. It preserves the narrow nature of the peaks. So here you see how the neutral exciton shifts. So it basically shifts much, much further than its line widths. And then we gain insights in all sorts of fine structure that we can now study as function of strain by kind of scanning our laser across this nanowire profile. And one effect that one can measure this way is actually quite tiny one, even it's a very basic and very fundamental effect in this material, is the fact that strain doesn't shift all bands equally, but there are changes in the fine structure here for WSA2 system in the conduction band. It changes this splitting. And as you can see, it's just an MeV or 1.5, but one can still measure it because, again, it's an encapsulated system with suppressed disorder and narrow lines. And then we do transport, or we do diffusion experiment here. So we excite excitons somewhere in the middle, and then we look how they propagate along the nanowire and across it. Yeah, so first, we turn the nanowire in a way that we look along the direction, and then we again see a very prominent increase of the area of the emitted light over time. So here we're talking about a nanosecond observation. I will talk a little bit more in the last part of the presentation what these numbers actually mean. For now, it's just something 1.4. Okay. More importantly, it's still diffusive transport. Yeah, so we have no ballistics, we have no saturation, we have no influence of non-linearities, so it's also pumped very gently. Just diffusive transport along the wire. But if we look across the wire, we see almost nothing. Yeah, so the diffusion coefficients which we extract are very small, they're close to 0. And of course, arguably, the difference to 0 is not that significant considering the noise. So all in all, we can say even at 5 Kelvin, we get something like 90% of anisotropy in exciton transport. So basically, excitons can move only in one direction. That's it. Interestingly, I mean, this happens at 4 Kelvin, but we go to room temperature. And people care about room temperature for many reasons. Sometimes you think applications. Another reason is that this is the region where interactions are strong with the lattice because you have a lot of phonons excited. But at room temperature here, interestingly, we see very similar anisotropy. Yeah, so the transport along the wire is relatively strong. The numbers are actually even higher. Across the wire is very small, maybe slightly negative, but this is something for a separate discussion. But the important point is the anisotropy is preserved. And it's not trivial. Why? Because we have a depth of potential of about 10 MeV. We know this also at room temperature. We can scan across, we see nothing have changed. But the thermal energy the excitons have is actually quite substantial. It's on this order and maybe slightly more. So something else needs to contribute. And one idea what it can be, and what for sure plays a role here, is the fact that strain does not only change the energetics, it also changes the dynamics. And in the recent years, there was a couple of works on the subject that strain actually can change, and in particular, suppress exciton phonon scattering in some of the systems. And the easy explanation, and a very cartoonish one I want to show you here, is the following. In many of these materials, the fact that you have many values that are energetically close to each other within the reach of a, let's say, optical or zone edge phonon, means that such processes as I show here, from one value to the next, play a big role and can determine mobility of electrons, but also excitons. And people saw it mostly not in diffusion, but in line widths broadly, at least in those early papers. But now strain doesn't shift all values in the same way. It doesn't even shift them in the same direction. There's values that go down, there are values that go up. And as it happens in this material system, this happens. The strain, sufficient amount, can push other values up. So certain channels that were allowed before, that led to momentum scattering, collision scattering, limited the mobility, are not present anymore. And in fact, if we evaluate the line widths here, we also see this effect that in the middle, the line width is narrow, the spectral one, and the sides and the line width is one measure for the scattering, if you think about Heisenberg relation. Yeah. So narrow lines means they're scattering, and in fact, we can think about something like a channel where the scattering is suppressed, and this is surrounded or smaller by regions of high scattering, in addition to the potential that is induced by the wave. And that helps to understand at least part of the reasons why we see this anisotropy at room temperature, even if the strain groove does not give us a potential depth that is higher than the KBT. So to summarize, I have shown you how one can use strain from gallium arsenide nanowires to induce quasi one-dimensional transport. And of course, we can discuss whether one can go to a true 1D, which would be a very interesting direction here. One can have diffusion and anisotropy basically 100%, so the excitons can move just in one direction, left and right. And the reason for this is that we have a static potential, but also the exciton phonon interaction is reduced. It's a bit of a subtle effect, but it seems to be quite important here. And with that, I would like to come to the third part of the presentation. Thomas, how much time do I have? Since you're here, I think still quite a bit.
You have to ask Andres. I mean,
Oh, I'm sorry, no, but your face popped up here, so I kind of was tempted. But I think I probably have like 10, 15 minutes. Okay. So yeah, here I would like to present you a study, a very recent one, on the nature of exciton propagation in the systems. And the study in our lab was done by Coulomb and Wagner, and the first experiments were initiated by Jonas Zipfel. We, with the help of, of Edith Witek and Jonas Sigler, we collaborated in theory with Michael Glazov and with Roberto Rosati and the group of Ermin Malic from Philips University, Marburg. So one can ask this very general question is actually, what is the nature of exciton transport? And one can ask it in the same way people would consider transport for electrons. And the limiting cases for excitons are the same. So on the one hand side, you have a picture of a semi-classical free propagation. And this is a process you can imagine for excitons, for electrons, for billiards balls, maybe, you know, for drunken people in a crowded place, for any classical particle that moves randomly in some direction, then it scatters randomly, change directions, move ballistically again, scatters, moves, And for quasi-particles and for excitons in particular, this is usually what people consider for Vanya-like excitons that you encounter in inorganic materials. Think gallium arsenide, think cadmium sulfate. Yeah. Oh, but Thomas, maybe you can turn your mic off then, because I hear you typing a little bit, I think. Thanks. Yeah. Cool. So that is the semi-classics. And on the other hand, you have another extreme. You have hopping. And hopping means exciton is immobile. It just sits somewhere on one of the molecules on some site in the system, maybe even a defect site, who knows. And then it needs excess energy to be able to move from one side to the next. A hopping process, a tunneling process, essentially. And this you usually encounter for Frankel-like excitons, so excitons that are localized very much in terms of their wave function, and inorganic semiconductors such as, for example, tetrazine. And in our field, usually, if you look at the literature, I think almost any literature that uses a model to describe exciton transport till, I don't know, quite recently, 2020. What broadly is assumed is this picture if the system is clean. Yeah, if the system is not clean, of course, you can imagine hopping, sure, but if it's about intrinsic transport, this is the picture people have. We as well. So if, you know, look in our earlier papers before, same game, we do a semi-classical idea of how exciton should go. And the reason is because over the years, it became more and more obvious that Vanya picture is probably the appropriate one. Yeah, so that we don't, even if the binding energies are high, we should think about excitons more like in gallium arsenide, just much smaller in size and much stronger in terms of binding. But one can put a question mark, of course, to this, and also ask oneself under which condition does this picture applies? Is it correct? Should we think along this way? And to do this, again, in theory, one would basically do the same thing we do for electrons. And it's always, if you think about transport, a very, very good kind of idea to go back to electron transport, because people studied it a lot in many ways. Over our technology is based on this. But to find out how the transport works without, let's say, applying magnetic fields or something of this nature is usually by looking at the temperature dependence. That is very, very characteristic for these two pictures. And for semi-classic, the description is the following. Diffusion, the way a particle propagates, scales with temperature. So temperature gives kind of a driving force, the kinetic energy. The higher the temperature, the faster the particles move. Divided by mass, the larger the particle, the slower it is. And then times scattering time. So the larger the scattering time, of course, the less it scatters, the higher the diffusion. The shorter the scattering time, the more it scatters, the smaller the diffusion. And in semiconductors, in particular, the scattering time as function of temperature usually has a very, again, characteristic behavior. It scales linearly with temperature at lower temperature because of the interaction with long wavelength acoustic phonons. And then as more and more phonons are introduced to the system, the scattering time starts to grow non-linearly and the diffusion is expected to decrease. And you should start with a relatively high value at 0 Kelvin. The hopping case is the opposite. There, the diffusion is expected to scale exponentially and be exponentially activated with a certain energy barrier for the hopping process, delta E, divided by the temperature. So it means that at lower temperature, you should basically have no diffusion, everything is frozen out. And then as you give some kinetic energy to the system, then the particle starts to propagate faster and faster. And these are the two kind of cases you will find, again, for Wagner type of excitons in clean systems at sufficiently high temperatures. And on the other hand, of course, for Frankel type states and pentasyn, tetrasyn, this type of structures, or in strongly disordered systems. But as easy it is to kind of go back to these dependencies and say, okay, we need to measure diffusion as a function of temperature, as challenging it can be experimentally. And the challenge is twofold. If we need to cool down, we need to make sure that this order is really, really taken care of. Yes, because even if we are left with a couple of MeV of this order, it will not help because we need to go down to very low temperatures and we need to have a clean system in terms of inhomogeneities. So this is first kind of challenge. The second one, if we think about excitons that couple strongly to light, we reduce the temperature. Most of the excitons go to low momentum states where they can efficiently radiate and the lifetimes become short. Yes. So then the system doesn't have much time to diffuse and propagate altogether. And these problems one needs to resolve. And luckily, nowadays, we can find systems that offer us both of these necessities to provide a clean experimental access to test this, the nature of exciton transport. And to do this, one can go to dark excitons and place dark in parentheses because there is some light that they can emit. But dark excitons and HBN encapsulated WSA2. Yeah, so encapsulation makes sure we have narrow lines. We get rid of disorder, especially the dielectric one. And dark states are long-lived. And we need long-lived excitons because, again, we need some time to be able to observe them, how they move. But luckily, dark excitons are not actually dark. So they are dark in absorption, for sure. They don't carry any oscillator strings. You try to excite them, it's very hard. You need a lot of light. They don't show up in reflectance and transmission, but they show up in luminescence. And over the recent years, the understanding in the community, especially having clean system with narrow lines, evolved a lot. So now we can basically, from the forest of peaks we were confronted years ago, now we can actually assign these peaks and understand what these peaks are and use them for observations as observables. And the transition we use here stem from recombination of dark excitons that are either spin forbidden. So here I use the two-particle notation. So you see KK, it means it's an electron transition from K to K. You see KK prime, it means it's an electron transition across the Brion zone from K to K prime to minus K. So those are intervalley excitons. Their recombination is momentum forbidden. This recombination is spin forbidden, but both can emit. This can actually emit directly in Z polarization, but both can emit with phonon-assisted emission. So they give some energy, and in this particular case, a lot of momentum to a crystal vibration, and then it can emit light. And this light can be detected. And you can see here kind of cuts from a spectra as function of temperature from direct recombination of a dark state in Z direction. We use sufficiently large numerical apertures to detect it, but also the phonon-assisted emission. And the phonon-assisted emission has this very characteristic asymmetric line shape, because it includes excitons that have finite center of mass momentum. And all the lines are quite narrow. So this line is about 1 MeV at lowest temperature. And this means from this symmetric broadening, we can directly extract the scattering time. That is important. We need to know what the scattering time is to be able to tell what the propagation mechanisms is. But of course, we also have access to exciton temperature, which is very good because we want to avoid any non-equilibrium situation. We want to know very precisely that our excitons are cooled down, and we just have a relaxed long-lived system to study. And this way we can get it. So if you look at the spectrum, as I mentioned, one can identify nowadays the states. There is some controversy regarding some of the lines that I did not label here, but these states are very well understood. And in an experiment, before we study diffusion, we can spectrally cut the emission from those resonances. And if we do that and we look at the area as function of time, so here, as you can see, we can have half a nanosecond easily to observe them luminescing. But the area changes for all sidebands, interlayer, in a similar way. So they all diffuse similarly, and that is also expected because the interaction with phonons that governs diffusion, for these conditions, we're talking 5 Kelvin, is the same. The number we get from this is 2.5 centimeters squared per second. And diffusion coefficient, so in many cases, one doesn't have a feel for what this number means because usually people deal with electron transport, but not with diffusion. But there is a relationship between the two. So, and this relationship is sometimes used because it's useful also for excitons, even if excitons are neutral. But that basically gives you an idea if excitons were electrons or if excitons were charged, what would the mobility be? What would be the mobility corresponding to a diffusion coefficient of 2.5? And in this case, it will be 6,000. Yeah, so that supports, again, the idea that we have very clean system in this case. We can look at scattering rate and from spectral broadening, and we find the linear dependence with temperature. Here, it's deconvoluted by a small inhomogeneous broadening on the order of just below 1 MeV. Yeah, otherwise, you will have an onset over here. And this linear dependence is something, again, it's a textbook behavior of exciton phonon scattering. It's also very much consistent with 2D Fourier spectroscopy results, even on earlier kind of first generation samples that can directly measure the scattering time, regardless of the inhomogeneous broadening. So this is the linear increase that we expect when excitons scatter with long wavelengths acoustic phonons. So now we have basically everything in place to predict how the diffusion should look like, just from the measurements, not from theory, just from the measurements. We take the semi-classical model, and we should expect a constant diffusion coefficient somewhere between 2 and 3. And in fact, actually, if you take deformation potentials from literature and calculate what diffusion should be, it will be somewhere in this range. So even quantitatively, there is a good match. It should be constant, as you would expect, again, for a 3.5 material. But the surprise comes in experiment. We look at the area change as function of time. And again, you can see it increases, of course, and it's more or less linear, it's diffusive. Here we have a little bit more noise. But even in this low temperature range, 5, 10, 15, 20, the diffusion slows and slows and slows and slows down. So the diffusion coefficient is what we should expect semi-classically at very low temperature, but then it goes down, 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 down. And this is a rather unusual behavior. Again, here I show you what we should expect. And obviously, it is not what comes from semi-classics. And here, again, the important thing is we have independent access to scattering time. So any process, any additional process beyond phonons, you can think about doping activation, something with defects, anything that will be captured over here, but it's not. Yeah, we just measure decrease of diffusivity even if the collision time remains linear. And obviously it's not hopping. I mean, this is something that again has to do with the fact that we suppress disorder. So how should we think about it? And if you consider this extreme cases of hopping and semi-classical transport, the quantities one needs to think about is the de Broglie wavelengths. So this is kind of the size of the semi-classical wave packet, as we learn in solid state physics courses. And the other one is the mean free path, so how long the exciton flies. And the semi-classic actually make only sense when the size of the packet is actually smaller than the mean free path. Yeah, so we actually have something that if we zoom out sufficiently, looks like a particle that travels along a line, then it scatters and scatters and scatters. On the opposite side, we have localization hopping, where the exciton basically doesn't move and just hops from time to time. And if we consider the numbers for the 2D materials, for the monolayer semiconductors, then we find that here the de Broglie wavelengths is actually very similar to the mean free path. So we have a rather unusual case for excitons, where the mean free path and de Broglie wavelengths at low temperatures, both are on the order of 30, 40, 50 nanometers, are almost the same. But what does it mean? I mean, does it mean we should have some, average between this? I show you here between these two curves. In fact, no. So again, we go back and we learn from electrons. So what physics can we expect in this regime? And what we can expect here, that when excitons goes and travels, and I use the semi-classical picture here to explain, what can happen is that it can start traveling in kind of loops. Yeah, so it can have trajectories that are essentially equivalent in terms of they are scattering, but they just go one time. It could go counterclockwise, it could go clockwise. It was predicted for excitons, never really measured, and people worked it out for electrons a long time ago, because it leads to a phenomenon called weak localization, and in some limit also strong localization, that exciton becomes localized in this loop if the relative phase relaxation time is sufficiently long. But as it happens in this type of systems, and our colleague Misha Glazov worked it out recently, the dependence on the kind of the scattering time and the relative phase relaxation time change with the temperature in a way that the scattering becomes more and more elastic, at least in the low temperature regime. And it means that if we consider quantum corrections, theoretically, in this relatively, well, simple maybe, yeah, perturbative approach, it should lead to a decrease of diffusivity. At some point, of course, it should go down, up again, because additional phonons are introduced. They lead to dephasing, and then we're back to semi-classics at room temperature. So this curve, in reality, if you include other phonons, should go up. But in the low temperature case, it actually decreases. The numbers here, 3.4, are similar to what we have. And that is something that is also observed. Yes. So this is a behavior that can be understood in this fashion, but qualitatively so. Quantitatively, of course, we would never be able to talk about weak localization just by the amount of change it's introduced. And the system, of course, is more complex. We have different values. They can start to contribute at some point that we, were able to figure out together with Roberto and Ermin. But the characteristic shape is similar, and it's obvious that because of the similarity of de Broglie wavelengths and mean free path, quantum effects has to play a role in this case. So we actually even can't properly think about a semi-classical system in this temperature range. So with that, I would like to conclude this last part, where I've shown you that the temperature-dependent diffusion of the excitons is actually quite unusual, even in monolayer samples. And I say even in monolayer because if you look at the literature now, people studying all sorts of very complex systems. We talk about heterostructures. There is, of course, ideas what should happen if we have a Moray superpotential, but it's relevant to understand the building blocks themselves. And if we try to do it, we find that the semi-classics that served us so well for 3-5 semiconductors, they don't work here. But hopping doesn't help. So organic crystals don't help to understand it because we have indication of quantum interferences. And the good news is, of course, while it's unclear how to properly describe it theoretically, and actually quite tough if we want to go beyond perturbative treatment. But it means now we can actually study quantum transport phenomena also for exciton quasi-particles, and we have an experimental platform to do so. So with that, I would like to conclude. I've discussed kind of the broad topic of exciton diffusion, monolayer materials, of course, tainted by our own perspective on the subject. The particular topics were strain-induced unidirectional exciton flow, and the whole kind of journey to understand the nature of transport of excitons, and in particular show that they don't behave classically as broadly assumed, including us so far. And then I would like to have a little bit of advertisement. So our group, which now moved and is moving to TU Dresden, we have new labs, new equipment, ERC grants, a lot of resources. We look for motivated colleagues to work with. There are open positions this winter, spring 2022 and beyond for postdoctoral researchers, for PhD candidates, maybe also for internships. If anybody should be interested, know somebody who could be interested, just feel free to apply. I will be happy to discuss the opportunities. Thank you very much for the invitation. I'm happy to take questions.